So this is still it's a general talk, but maybe towards the end I'll get to this frequency count problem. So I'm going to start with some general things. So let's talk a little bit about dynamic data structures. A dynamic data structure is a data structure where things are constantly changing. So there are special data structures to store such things. If you were to store in a simple data structure, you'll see that things start to go bad. For instance, if you store, if you have a dynamic data set and you want to store it in an unsorted array, inserting things, it can be very fast because you can throw it anywhere. Anyway, it's unsorted. But if you want to either search for something or delete something, then it becomes very expensive, right? Same thing if you have a sorted array, now search can become fast. And hi, come on in. Let me restart this. So we're talking about something called dynamic data structures. A dynamic data structure is a data structure that's constantly changing. Okay, a simple, most of you are used to things like arrays and linked lists and trees and such. But you'll see that many of these data structures are good for some operations and not good for some other operations. So for instance, if you have an unsorted array, then it's great for inserting things because you can put things anywhere you like. It doesn't really matter. You're not really maintaining it in any way. But searching for something or deleting something is very difficult. And so it can take you order n time in order to make that happen. On the other hand, if you have a sorted array, then the advantage is that because it's sorted, you can do binary search. So searching is very fast. But if you want to insert something, you may have to move things around and keep things in order. And so therefore, inserting and deleting becomes very expensive. And then linked lists have similar issues. If you have an unsorted linked list, you can insert very quickly. In sorted linked lists, it's very difficult to go and find where to put it. So even search becomes expensive. So almost everything, all the operations end up being too expensive. So that's how people started looking at tree structures, because tree structures were a good compromise between storing things in an array versus storing things in a linked list. In a linked list, you could insert things in between very efficiently, but finding stuff was difficult. Whereas in an array, you could search for something quickly, but you couldn't insert something very efficiently. You had to move things around. And so the trees helped to get over some of these problems. And with binary search trees, you can do search, insert, or delete in time proportional to the height of this tree. And binary search trees are very useful because they organize things in a nice way. And if you want to search something, it'll tell you whether to go left or right in order to search for, in order to continue searching. So binary search trees are great. Their time complexities are great if, in fact, the time complexity is proportional to the height of the tree. But the height of the tree can be very large if you are not very careful. And this happens especially in dynamic data structures where you may be inserting and deleting things in some bizarre order. If you don't insert things in a nice order, what might happen is that the tree might become very unbalanced, and so search and insert and delete could become quite expensive. So the height of the binary search trees can be crazy large. And in order to address that problem, these balanced binary search trees were invented. And there, what you know is that search, insert, and delete all become very, very efficient. and you can solve them in log n time. And that's because the height of the tree that you end up with is bounded by log n, which makes all these operations efficient. So let's look at a simple example of a binary search tree. Here's an example of a binary search tree. The simple idea is that if you look at any node and follow its left branch, you'll get values that are smaller. If you follow the right branch, you'll get values that are larger. So that's 20. All these values are smaller than 20. All these values are larger than 20. It doesn't matter which node you pick. Any node you pick, the left side will give you values that are smaller, and the right side will give you values that are larger. So at every node in the tree, you have this nice property that if you want to look for smaller values, you go to the left, and if you want larger values, you go to the right. So that's how things get organized. And search is very, very efficient. If you want to search for, let's say, 23, you start at the top, and you know that 23 is larger than 20, so you'll go to the right subtree, because if at all it's to be found, it'll be in the right subtree. Then you'll hit 40, and there it'll tell you know that 23 is smaller than 40, so you'll go to the left subtree and search here. Then you go to 30, and 30 says again 30 is larger than 23, so you'll go to the left, and you'll end up over here where 23 is still smaller than 28, and you'll want to search in its left subtree, which in this case is empty. So you know at this point that 23 is definitely not in the tree, and the search becomes and the search can be ended. What you did was you started at the top, and at every step you went one step lower in the tree until you hit some kind of a node where it didn't have an appropriate child for you to search. So essentially the time complexity of search is proportional to the height of the tree. This is a specialized binary search tree. It's called a red-black tree. And a red-black tree has this nice property that every node is colored either red or black. And it has this additional wonderful property. Well, it has two other interesting properties. The second property is that a red node will never have a red child. Okay, so you'll never see two red nodes in succession. All right. So if you see a red node anywhere, both its children, if any, would be colored black. Okay. Then finally, the last and most important property is that if you start at the root, and if you make your way down to some leaf of the tree, then every such path will encounter the same number of black nodes. So if you start at 20, if you take the leftmost branch, you would encounter 1, 2, 3 black nodes. Now, it doesn't matter which path you take. You can go 20, 11, 15, 12, and 13. That also has 3 black nodes. If you go 20, 11, 15, 18, that also has 3 black nodes. So every path you take from the root to a leaf, it'll have the exact same number of black nodes. Ensuring that this happens, by the way, this can be nicely maintained. There are algorithms to keep the tree in such a way that these 3 properties are always satisfied. Even if you insert and delete things, you can keep these properties satisfied. So you don't have to worry about this because there's Java code or Python code out there. You just plug it in and it'll do this magically for you. But the nice thing is that the height of these red-black trees, if these 3 properties are satisfied, they're always going to be roughly of the order of log n. And that ensures that all operations like your search and insert and delete are very, very efficient. And in particular, they're all going to be achievable in log n time. Okay? So these are the basics of dynamic data structures. Ultimately, the red-black trees are sort of the pinnacle of what you would need to do in terms of making sure that you build a data structure where you can You can insert and delete things at will and yet be able to search and do these operations very efficiently. Okay? So that's what red-black trees are good for. And you will see that they do your three basic operations very, very efficiently, namely search, insert, and delete. Unfortunately, that's not going to be often enough. In many cases, you may need additional queries. And that's where we need to do more. So here is a simple example of a new query. Supposing I wanted to ask you how many items are there in the range 6 through 14. Okay. So, well, you can kind of stare at this tree and see that there is 1, 2, 3, 4, and 5. There are 5 nodes in this tree that are in the range 6 through 14, right? Now, how do you figure this out? Well, one way to do this is to go and look at the entire tree, find all the values between 6 and 14, and just count them. What's the big deal? Well, the big deal is that you would have to look at the entire tree in general. So if I were to ask you for the number of items in the range 2 through 45, you would have to pretty much go and look at the entire tree. And this tree is assumed to be very, very large. So your time complexity essentially goes through the roof, and you want to be able to do this faster. So question is, what can I do in order to answer queries like this as quickly as possible? What we saw was that it all depends on what range you pick, and if you pick bad ranges, you might have to look through the entire tree, and this tree has n nodes, so you might have to look at, it could be a linear time operation, order n time operation, and ends up becoming way too expensive. So if you want to be able to answer such range queries very efficiently, then you have to do something more to this tree. And one of the first things that people looked at, that people used, was to augment these red-black trees with additional information. And in general, if you want to speed up more and more operations, you have to add more information to the tree, make it richer in order to be able to answer some of these queries as quickly as possible. So the first thing that people have tried is to augment each of these nodes with what is called as size information. Here at each node, I've added a size information. This size information turns out to be, what's that? The size information turns out to be the size of the subtree that's rooted at that node. Give me a second. So the subtree that's rooted at 13 has only one node, which is itself. The subtree rooted at 12 has only 2 nodes, and so we store the number 2. If you look at the subtree rooted at 10, it has all of this, which has 4 nodes in it. If you look at the subtree rooted at 40, then this side has 5 nodes, this side has 1 node, and then it has itself. That would be 7, right? So if I could somehow store this information of size in each node, this turns out to be extremely valuable in answering lots of useful queries, especially related to the kinds of questions we asked on the previous slide, which is how many items are there in the range 6 through 14. Now, it turns out that if I can store this size information, I can actually do this somewhat efficiently. And the way that works out is something I'm going to show you next. Are there any questions so far? Or is this flying way over your heads? Are you okay with this? Yeah? Okay. All right. So what we do is we want to know how many items are between 6 and 14. Let's just pick these 2 numbers. We could have picked any numbers we liked. It doesn't really matter what we pick. Okay? Then what we're going to do is to first locate where 6 is. All right, 6 is located over here. So I'm just going to highlight where we are. So that's 20. Then we have 11. Then we have 10. Then we have 5. And then we have 6. That's where 6 was. I'm just showing the skeleton of the path we took in order to locate 6. Next, I'm going to try and locate 14, which I know is not in the tree, but that's okay. I'm going to search for it. On this side, I have 40. Then I have 30, because that's where I'm going to go. And then I am going to go to, oh, sorry, what did I do? No, wrong. I shouldn't be going this side. 14 is to the left of 20. So I'm going to go left to 11. Then I'm going to go to 15. And then I'm going to go to the left of it to 12. And then I'm going to go to the right of it, which is 13. And then somewhere here, I'm going to stop because 14 is not in the tree, right? So I want to know how many nodes are somewhere in between this point and this point in the tree. Okay. All right. Now the question is, how do I do this? And in order to do this, it turns out that I'm going to use the size information. And you'll see how the size information becomes useful. So let's write down the size information. Remember, we had 1 here, 5 had 3, 10 had 4, 11 had 9, 15 had 4, 12 had 2, and 13 had 1. Right? That's what we had for the size information. It turns out that by selectively adding the right things, I can figure out how many items are in the range 6 through 14 in this tree. And let's see how that's done. By the way, the first thing I'm going to also mark out is that if I want to look for the values between 6 and 14, then this node is important because 6 is on one side and 14 is on the other side. Okay? Which means everything on the other side of this tree, of this node, is completely useless to me. I don't even care what's there. I don't even care how many items are there. So all this stuff is totally useless to me. Okay? Because I am focused on the range 6 through 14. Right? So I can ignore all of this. I can ignore the fact that the node 20 had a size information of 17. I don't care, because that's outside my range. So I know that this is the critical node. I know that this subtree had 9 nodes, but even that 9 is not important because it may include things that are outside the range 6 through 9. So I'm not going to focus on that right now. I'm only going to count all those things, all those subtrees that are completely in this range 6 through 9. So I go and look for 6, and let me use a different color. So what I do is from here I go to the left child, because that's the path I'm going to take to find 6. So this is the path I need to take to find 6. As I do so, I look at how many things are, I know I want to go smaller than 11, right? I know I'm going to go, so actually let's start with 6. If I look at 6, it has no subtrees, and so therefore the left subtree is empty, the right subtree is empty, so therefore there is only one item so far in this subtree that is in the range 6 through 14. So I'm going to keep track of one that happened at node 6. Then I work my way up to this node with value 5, and here I've already counted the stuff on the right subtree, and whatever is on the right subtree is going to be smaller than 5, which means it's going to be smaller than 6, which means I don't have to count anything. So at 5, the contribution is going to be 0. Then I work my way up to 10, and here I've already counted everything that's smaller than 10. It has nothing on the right subtree, so the only thing that I have to count is itself, and so at 10 I'm going to get a contribution of 1. Then I go up, and I've already counted everything that's on the left subtree. I need to count something on the right subtree, but I know that part is going to be counted separately. So I only have to count one more node, and that's number 11, and I count 1. So this gives me all the values that are in the range 6 through 11 in that subtree. Okay. Next, I'm going to go over here and start to look for 14. Remember, this is the node where it branched off, where 6 was on one side, 14 was on the other side. So I've already looked at everything on this side, and I've counted everything that's smaller than 11 but larger than 6. Okay, so this range 6 through 14 will go from 6 to 11, and then from 11 to 14. So 6 to 11 we've already counted, that's over here, and we know that there are 3 values that are in the subtree. Next, we're going to go to the right subtree of 11 and count all the things that are smaller than 14. Now 11 itself is smaller than 14, but it has already been counted, so I'm not going to count it twice. So I go to the right subtree, I go to 15. Now 15 is outside the range, and so therefore I won't count anything there. At 15 the contribution will be 0. At 11 also the contribution will be 0 because it's already been counted. Then I go make my way to 12, and at 12 I know that 12 itself is smaller than 14, so I have to count 1. It doesn't have anything on its left subtree, and then I know I'm going to go to the right subtree, so I'm going to count more as I go forward, but I'll just count 1 for 12 itself. Okay, then I go to 13, and at 13 it doesn't have a right subtree or a left subtree, and 13 itself is smaller than 14, so I'm going to count 1 for it. So essentially I've counted all the things that are between 6 and 14. In this case it's going to be 5, but the time that I spent for it is simply the time that it took me to go search for 6 and search for 14, and along the way I counted a bunch of things which I added up. Now what you also need to know is that in general there could be a lot of stuff that may be hanging off of here. So for instance, there could be an entire subtree here that's smaller than 5. Even if it did, it won't contribute anything over here because those values are going to be smaller than 6. Same thing over here, if there is a left subtree to 6, it's not going to contribute anything because those values are smaller than 6. If there are things that are larger than 6, then you would have gotten a different number for this node, and you would have known what the size of that subtree is, and you would have counted it. Then over here, if there was a subtree for 10, a right subtree for 10, which had a bunch of items, then all those values would have been between 10 and 11, and they would have been counted over here as part of the subtree of that's rooted at 10. So all it's saying is, with the process that we did, if we count these carefully, then we would know exactly how many items are between 6 and 14. It's a little complicated, but overall it's very intuitive. And all we are doing is, as we go from 6 to 11, we are only looking at the right subtrees. Then as we go on the other side, we're only counting things that are in the left subtree. So by doing this, we would know exactly how many items are in the range A through B. So let me redraw this picture. We start at the root. We get to a point, as we do a search, we get to a point where supposing we want to know how many items are in the range A through B. We first get to a node where somewhere here is A and somewhere here is B, which means this value here is between A and B. If we start at the root, and if the root is either larger than this or smaller than both of these, we know it's not really going to give us useful information. So we work our way until we get to a node where the value is between A and B, and in this case that was number 11, because 20 was way outside the range. 11 was the first time that was in the range, so we stop there, and then we do the next step, which is we find the two paths, one to A and one to B. Okay, and along this path we are going to add things, and that's how we will get the number of values between A and B in this tree. And the way we do that is for every node we see if there is a right subtree. So for any node for which there is a right subtree, we add some things, and the sizes of all these subtrees will simply get added to, because these are all values that are between A and B. And on this path, on the second path, let's make this the red path, what we'll see is that we want to look at left subtrees, and we take the sums of the sizes of these left subtrees and add them up, and that's how we get the number of values between A and B. Okay. All the sizes of these subtrees, you don't have to go and look through them because they are already stored at the roots of these subtrees, so they're easy to figure out, and all we have to do is to add them up. And so the time complexity is simply dependent on how many nodes we visit along this path and along this path, and as we know, that cannot be worse than log n because each of these searches takes only log n time. Okay, is this making sense? Little complicated, but we can answer these queries quite efficiently. Okay. Now there's also a simpler query that one can ask. One could ask how many values are smaller than 12 in this tree. Okay. So we know 12 is somewhere here. Or let's actually try something more complicated. Let's say how many values are smaller than 31. Okay. If we were to do this in a brute force manner, we would have to go through the entire tree, find all the values that are smaller than 31, and that would be our answer, right? We would prefer not to do so. We would prefer to figure that out just by counting. Now, the path from the root to 31 is very, very clear. We would go from 20. We would start at 20. 31 would be bigger than it, so we would go to its right subtree. We would go to 40. 40 is larger than 31, so we would go to its left subtree, which would take us to 30. And then 31 is larger than it, so we would go to the right subtree, which would be 35, and then we would go to its left subtree, and that's where we would find 31. Okay. This is the path we would take if we were to search for 31. Now this is something we would have to do if we want to find how many items are smaller than 31. We would have to at least first locate it. But we would like to avoid work that's a lot more than this. Okay? And remember that the time it takes to search for 31 is the height of the tree, which is log n. We would like to spend at most log n time in order to find how many items are smaller than 31. How do we do this? Now this is where it turns out to be quite simple. What we do is we start at 20 and we ask how many items are smaller than 20. Well, we know that answer because we just go to its left child and look at its size. That size is how many nodes are here, right? So we know that there are 9 items here. So I didn't have to go and search that. I could quickly figure this out. right? So I know that there are 9 items smaller than 20, and there's 1 item to count for itself, right? So far, I know 10 items that are smaller than 31. Are we good so far? Then we go over here. We know that 40 is already larger than 31. We don't have to count it. So we skip that, and then we move on to 30. Over here, 30 was large, 30 is smaller than 31, and so we ask how many items are smaller than 30 over here? And we know the answer is 1 because its left subtree has size 1. So there's 1 item over here. And 30 is smaller than 31, so that's 1 for itself. Then we go over here, and 35 is already larger than 31, so we ignore this, and we go to its left child. Now 31 is exactly what we wanted, so we count 1 for itself, and then check if there is any left subtree that has stuff in it. And in this case, the left subtree doesn't have anything in it. So now we actually have the right answer for how many items are smaller than 31. The answer is we take this 9, we take this 1, we take nothing over here, then we take another 1 and 1, and then we take a 1 for 31. So that's the answer for, well, I actually included 31. If you don't want to include it, it's going to be 1 less. So it turns out that there are 13 items that are less than or equal to 31. And you can verify this. Yeah?
Because this seems like an easier query to do. We can just do this query for 14.
Yeah.
And this query.
That's correct. So the reason I didn't want to do that was because we're going to do another problem where we're going to need something more complicated. So that's why I didn't go through the easier one. So what Ricky is suggesting is, in order to find how many items are in the range 6 through 14, figure out how many items are smaller than 6, figure out how many items are smaller than 14, and subtract 1 from the other, right? That's easily done. But I wanted you to see this complicated one because we're going to need that in a few minutes. Is this making sense? Yeah? Okay. So let's see how we can make life more complicated for ourselves. Yeah, I'm going to. So there's this nice problem called k-frequent values. Let me show you the problem first. Yeah, here it is. Where's my mouse? Okay, so here's the problem. I suggest you quickly read it. I'll give you a couple minutes and then we can discuss this. Oh, what happened here? Sorry. Oh, I have to get out of this, I see. Okay. All right, take a quick look. Okay. Okay, so make sure you've read the first 3 lines. It says that you're given a sequence of integers, and these integers are in non-decreasing order. That's short for saying what? It's short for saying it's almost increasing, but occasionally you may have repeat values. Okay, so So the sequence might look something like this: -1, -1, 1, 1, 1, 1, 3, then 10, 10, 10. So it never decreases, but sometimes it doesn't increase either. Okay, but if it increases, it's going to stay up there. Fine. So this is our sequence, and now you're asked to do what? You're given lots of queries. Okay, and the queries tells you the queries are for you to figure out what is the most frequent value. Okay, so if my query says find me the most frequent value in all of this, you're going to say it's 1, because there are four copies of 1. All the others have fewer copies, right? Are you good? If I shorten the range and if I go from here to here, then I may have 1 copy of 1, 1 copy of 3, and 2 copies of 10. In which case you should be answering that the most frequent value is 10. So depending on what range you're given in the query, you may have a different answer. Okay. So question is, how in the world are we going to solve this? Sorry, it's back.
It went back.
Yeah. Then they give you a little bit more about how this input is specified. Ignore all that. So you just have to focus on the top 3 lines. Okay? All right. So everyone understood the problem. That's the problem. And the question is, how are we going to solve this efficiently? The rest of that problem description tells you that you're going to be asked lots of queries, which means that each query needs to be answered as efficiently as possible. Otherwise, you're going to be in trouble.
Someone just asked that you're supposed to output the frequency, not the element that is most frequent.
Is it? Determine the most frequent value. So they're asking for the value, not the frequency.
The number of occurrences of the most frequent value. So like in your example would be 2, since 10 occurs twice.
Oh, over here, I see. Okay, fine. So yeah, they miswrote at the top there. It says determine the most frequent value. Okay, fine. Thank you. So all right. Our job is to take a bunch of values, keep track of their frequencies, and then also figure out what positions they're in. And then if somebody asks you a query, your job is to quickly tell them what's the frequency of the most frequent item. How are we going to do this?
So maybe first we want to find a repeating value.
Sorry?
First we want to find a repeating value.
Okay.
And then we want to find the size from like when it starts repeating to when it doesn't repeat anymore.
Okay. So let me simplify the problem a little bit for you. Okay. Let's say that I ask you a simpler query. I'll give you a number, and your job is to tell me its frequency. So if I tell you 1, your job is to say it occurs 4 times. If I give you the number 10, your job is to tell me it occurs 3 times. How do I do this?
Can we use anything?
What does that mean?
For example, like let's say if we're iterating and we come.
Of course, there's a naive way to do this. I can look through the whole array and count it. I mean, of course, anyone can do this. Obviously, we don't want to do it because the frequency may be very, very large. So, and we don't want to go through the whole list, right?
balance binary search tree, and for each value we can store count of it?
Yeah. So the reason for telling you about red-black trees and balanced binary search trees was to be able, for you to be able to think about solutions like this. And so here's the suggestion, right? So the suggestion is to go back to your red-black trees, right? But along with each item, store its frequency. Okay? So now if I ask you for the frequency of any item, you just go search for the item, and along with it, you've stored its frequency, and you just report this. Right? Simple enough. Is that clear? So I can quickly report the frequency of anything. And so my tree might look something like this. So let's say this is my data set. I have 4 copies of 2. I have 5 copies of 5. I have 7 copies of 6, and so on and so forth. So it's a large array, right? And now if I ask you what's the frequency of 18, you go and search for 18 just like you were doing a binary search tree search, and simply report the number that's stored there. In this case, that would be 11. Is that clear? And you know how to search for 11 because it's a simple binary search tree. You look unhappy. You have a question?
Me?
Yeah?
Oh, no.
Okay.
I'm speaking.
Okay. All right. So since it's a regular binary search tree, you just go and search for 18, and then you report the number that's stored there. And that'll tell you its frequency. However, yeah.
Sorry.
Go ahead.
I thought we were going to try to find the value that had the most frequency value.
We're getting there. We're getting there. I simplified the problem for you first. We'll steadily make this harder for you, and then see how it goes. Right? So the next thing is, what if I want? Yeah. So let's say we solve we answer the query that Andrew mentioned. What's the most frequent item in this whole list? How do you figure this out? And if, by the way, it may be useful for you to think about this as a dynamic structure where you're constantly inserting and deleting items. Okay. So if I want to insert a number 23, well, 23 is not there, so you would go and insert it just like you would insert into a red-black tree and make its frequency 1. If you wanted to delete a 28, you would go find 28 and you would reduce its frequency by 1. So inserts and deletes are easy. Searching is easy because it's simply a binary search tree search. And come on, why does it keep doing this? I have to change the settings somewhere.
Can I organize a red by tree by frequency instead of?
Yeah, that's what I was thinking. But then you have to make it entirely.
Yep, it doesn't matter.
Well, you could do that, but then if you wanted to update the frequency of something, how are you going to find it?
Yes.
Right? So you have to keep that in mind. You can't just focus on one query and let all other queries go to hell, right? You have to keep them all efficient at the same time. And so if you're going to reorganize, you have to think about how other operations get impacted, right? Where is my, it's not here. Okay. Screensaver. I think that's where it's going into, right? What is this? 20 minutes. It's on 20 minutes. What's the problem? Ah, annoying. Okay. Right. So organizing things by frequency values is not a great idea for the reason I just said. Namely, If I wanted to update something, I cannot. Okay? So in order to find 91, and if I want to do this quickly, what's the way to do so? How do I find where this largest value is hidden?
What if we had another attribute to the tree that's like max
Max of what?
of frequency
Where?
in every node?
In every node, you're going to store 91, which is the largest
No,
here.
As we're making the tree, we update the max frequency.
Define for me what you mean by max. It's unclear.
So each number has a frequency value.
Right. So right now, the largest here is 91. You agree with that, right?
Yeah, for example, let's say for the first node it's 10, right? So we start with 10.
What do you mean first one is 10? I'm not following
Our
it.
root node has
Ah.
a frequency of 10, right?
Okay.
We insert 11 at a frequency of 3. 10 is bigger, so we leave 10 as our maximum attribute, right? Then we insert 40, and then 17 is bigger, so we change the attribute to 17.
All right. So yeah, let me explain it differently. Okay. So one way to organize this is we add an additional piece of information at each node in the tree, where you would have not just the frequency of this node, but it'll be the largest frequency in the subtree that's rooted there. Okay. So for instance, over here, the subtree, there's nothing else in this subtree, so 7 is the highest frequency you've seen. But if you go here, the largest frequency you would have seen at this point in the subtree would be the largest of 5, 4, and 7, so it would be 7. Over here, it would be 11. Over here, it would be 14, and so on and so forth. So at the root of the tree, you would obviously, because of this side, you would have 91 percolating up. So at each node, you're only storing not everywhere, the maximum everywhere in the tree, but only specifically in the subtree rooted at that tree. Now the advantage of dealing with the subtree is that if you were to insert items or delete items, or if you were to change the frequency of some items, then it's all happening in appropriate subtrees, and so the values could be updated as needed. Otherwise, updating the values becomes way more difficult. So at each node now, we have two things we are storing. That's how we are augmenting. We're storing the frequency of that particular item that's stored in that node, and also the largest frequency you're going to find in the subtree. Okay? And you don't have to really know where it's going to be found, because I can easily figure out whether to go right or left, because each of those are also storing the largest frequency in that subtree. So for instance, if 91 is stored there, it's clearly not stored over there, because 91 is not found in this subtree, but it is found in this subtree. So here also you would have 91. Okay. Maybe I could annotate this and show you. Oh, but the annotations are only in Zoom. Here, yeah. So you can see that I would put 91 here. I would also put 91 here. And I would put 14 here, because that's the largest on this side. And can you see all that? Yeah, good. And of course, 91 won't be on this side, but it will be on this side. And then it will be over here. On this side, it will remain as 13, and so on and so forth. So you can put these values on each node, and now you have two pieces of information instead of one, and you can now efficiently answer the query, what's the largest frequency you have anywhere in the tree? Well, I could also ask, what's the largest frequency in any subtree based on the information that I've stored? But what if I start to ask, what is the largest frequency for values between 6 and 14? Okay. Now it gets tricky because I have to, or let's try 6 and 14 is fine. So I go through the same 6 and 14, and I want to ask, what is the highest frequency you have for any value, any valued item in the range 6 through 14? Well, it turns out you're going to do very similar analysis to what you did. Okay, but each time, instead of adding things up, you're going to find which is the largest. Over here, we were adding the numbers in order to count, right? When we were doing how many items are between 6 and 14. Now, instead, we're going to look at what's the largest you can find there. Okay. So let's see if we can do this computation. So we want to find the most frequent item that's in the range 6 through 14. Okay. So let's see. Over here, we don't have. Yeah, that's fine. So let's put down the values that we would find here, right? We would have 91 over here. We would have 14 over here, right? We would have 14 over here. We would have 7 over here. We would have 7 over here. We would have 11 over here. 7 over here, and we would have 7 over here. This is what we are going to get, right? Remember, these are the values of the largest frequencies you're going to find in the subtree. Fine? So now if I ask you what's the largest you're going to find between 6 and 14, you're going to do something similar to what we did before, and you get all these values. You'll get similar values to what you did before, except that instead of adding them up, you're going to do a maximum. Okay? So at 6, you're going to have 7, right? So we write down 7. At 5, we're not going to look at anything, okay? Because we've taken care of it, and 5 is outside the range. Then we go to 10. And there we're going to get 11. Okay. And then, well, no, actually that also is not right. Well, you have to find, no, that's fine. Okay. And then we go to 11, and we're going to get the highest, which would be 14, which may actually be outside the range. So we won't count it there. We'll take care of it later on when we go down the right subtree. So this one will be nothing. We will ignore this. When we go to 15, 15 is outside the range, so we're not going to worry about it. When we go to 12, 12 is in the range, and we'll find that its frequency is 2. So its largest one there is going to be 7, and then 13 is also going to give you a 7. So we'll get a bunch of numbers, and we take the largest of all of these. And in this case, that would be 11. And you can verify that between 6 and 14, 11 is the largest frequency we get. So we didn't go and search through subtrees and subtrees. Instead, we just touched the subtrees at the top, figured out the values, and used it for our computations. All right, now let's go to the harder problem, which was there on the problem that we looked at, which said, I give you a range, and this range is not range of values, but it's range of indices, and your job is to find me the most frequent item. So for instance, I think the array that they had there was -1, -1, then there were 4 ones, then I think there was a single 3, and then 3 tens. Right? So you had an array like this, and then you'll be given queries. The queries would be I'll give you a range that goes from here to here, and your job is to tell me the most frequent item. Or the range might be from here to here. Your job is to tell me what the most frequent item is. Okay. Of course, for this range, there are 4 ones, and so the answer would be 4, which would be the frequency of 1. And in this case, the frequency would be 2, because 10 has a frequency of 2. Fine? So, how do we now tackle this problem?
So if you're given some sort of range, you have to find like the first number that is completely in this range.
Yeah.
For the first query would be 1.
Yeah.
And then the last number that's complete in the range, which is 3.
Yeah.
And now we can use the query that you made up over here
Yeah.
to answer that part. That's number 1. But the second thing is numbers that don't fall completely within the range,
Yeah.
which you have to answer separately.
Which you have to
Just
kind
the
of deal with them
difference.
especially. That's correct. Yeah. So it turns out that the techniques are very similar to what we said over here. I'm going to show you some pictures which modifies this problem a little bit more, and what you're going to see is that the strategy is always the same. We take our trees and we massage them in ways that will help us to answer the queries that we really want to answer. Okay, and that's how you get to you make these things to work. So. So think about this problem. Let's say that we have one strategy is to take this list, okay, and convert it to a set of frequencies. Okay. So in this case, let's say that there are 21 ones, 9 twos, 3 threes, 6 fours, 14 fives, and so on and so forth. Okay, so we could change the array of values into a list of frequencies, and since they are in non-decreasing order, we know that this value is going to be smaller than this value is going to be smaller than this value, not the frequencies, the actual values, right? So I could then have 2 arrays where one has the list of values and the other is a list of frequencies. In this case, I've shown you as 1, 2, 3, 4, 5, 6, 7. In general, it could be any set of increasing values. I could add a third array that says where does this list start and where does the next one start, and so on, so that I would also have index information. All of these are utilities, but we don't need all of them. We're going to try and explain with this. Now here is the first idea. What we'd like to do is to turn this into a tree. Okay, and here's a possible tree. So we take all these values and put them at the bottom of the tree, make them leaves of this tree, and then we build a balanced binary tree on top of it, right? So these 2 would get included in this range, these 2 would get included in this range, these 2 in this range, these 2 in this range, and then all 4 of these would get included in that range, and then all 4 of these would get included in that range, and then there would be one at the top that would include all of them. Okay. What we've done is these are also called segment trees and so on, but you don't need those technical terms. It's a simple organization of the data that you have, where I've taken the items that I have, okay, and I have put them into a clean binary tree, and now I put all the frequency information at the bottom. And what I will have here is the larger of the 2 over here, larger of the 2 over here, larger of these over here. And then at the next level, you have the larger of 21 and 6, and the larger of 14 and 7, and then up there is the larger of 21 and 14. Okay, so you see that all this information can be built into the structure right at the start. Fine. And now, how can we find the maximum in a certain range? Well, we may need some additional. No, we have all the information we have. Right. Yeah. So now we can take any query and try and answer what's the most frequent value in that range. But what are the queries like? Let me see. Right. So this won't get to the indexes. I'm trying to solve a different problem here. Let me see if this can still be adapted for what we need. What did I do here? Right. So this is the array we start with, right? Here I've taken a different example. I have 2 1s, then 4 3s, then a 6, 3 9s, a 15, 3 24s, and a 39. I have converted this into an array that says I have 2 1s, I have 4 3s, I have 1 6, I have 3 9s, 1 15, 3 24s, and 1 39. Okay. And then I've built the tree that I showed you on the previous slide, taking 2 at a time and building your binary search tree, right? And in each case, you can see that this is a range that goes from 1 to 2. This is a range that goes from 3 to 6. This one goes from 1 to 6, but it has information on where it breaks. And same thing over here, and so on and so forth. And now you have all the information that you need with appropriate frequencies. So now we can try and see what happens if we pick a certain range and figure out the most frequent item. All right, let's take some simple ones first. Let's say we want to go from location 7 through 14. So if we go from 7 through 14, the most frequent item is either 9 or 24. Actually, let's go to 13. So let's go to 11 so that it's a simpler answer. Yeah. Okay. So if we go from 7 through 11, we know that the most frequent item is 9, right? And the frequency of 9 is 3. The question is, can we figure that out from that table there? All right. So in order to go from 7 through 11, first we are going to locate 7, then we are going to locate 11, and then we are going to look at the frequencies in that range and figure out the best one. So in order to locate 7, we start there. We know that 7 is still here. We know that 7 is here. We know that 7 is here. And so it's going to include this one. This is the place where we want to start. Of course, I picked these numbers deliberately to include entire ranges and not the parts of the left end and the right end. We can do that later. So we want everything starting from here, and then we want to go to 11. 11 needs to go this side, this side, this side, so it's everything from here to here. Okay? So if you want the largest value between this and this, we do something similar to what we did earlier. Namely, we're going to take a left branch and a right branch, and each time we're going to figure out what is the best. So we start over there, and then let me draw that picture here. So we start at the top, we go to the left, then we go to the right, and then we go to the left. That's what we have for one direction, and for the other direction, we're going to have to the left, and then to the left. That's where we go from between here and here. Now, on the right side, we do very different things from what we do on the left side. So, so over on this side, whenever we take a right turn, we're going to see if there is a right branch that gives us any larger frequencies. So over here, we'll see that the larger frequency comes from this side, which has a frequency of 3, and so we're going to count a 3 for this guy here, and we're going to count a frequency of 1 for this guy here, and so the largest frequency is going to be 3. We don't count anything over here because we're doing a right turn. Okay. Same thing over here. Anytime we have a left turn, we're not going to count it. But if we did a right turn, then we would count the values in there, which means all of these don't contribute anything. We just get down here and we'll get a frequency of 1. And so we take the largest of 1 and 3, and the answer would be 3. So that's how we get the highest frequency for this range from 7 through 11. Next, we'll do the more complicated case of dealing with parts of the start range and the end range. So if we were to start, let's say over here at 3, so let's say we want to go from 3 all the way to let's say until 12. So now the problem is that we're going to be in the midst of, well, this one is fine. No, let's take 4 then. So we're doing parts of a range. Then let's go up to not 12, but to 9. Yeah. So if we want to go from 4 to 9, then we have 3 3s, a 6, and 2 9s. The most frequent item is 3s, and its frequency is also 3. How do we figure that out? We'll start from there. We'll first look for 3 and that would take us all the way to here. But when we stop here, instead of the frequency of 4, we're going to take a frequency of 3 because we know only that part of it lies within our range, right? And then we're going to make our way up, and we know that this came from here, so it's not going to change. Then we go over here, and again, we're still within the same region, and so that's not going to impact us. We're going to leave it as 3. And then we're going to go down here to see if we have anything better. And before we do that, we have to go all the way up to 9, which means we're going to go to the right side. If there is any larger frequency over here, it would have contributed for something. So we would get 3 from there, 1 from there, and then 2 from here, because only part of this range is being covered. And of these, the largest is 3, and that's what we would report. So again, you see that we can use complete subtrees and speed up the computation. So overall, the picture becomes very similar to what I showed you here, where we take a left branch and a right branch. In the left branch, anytime there is a right subtree that's unexplored, we just take the value from its root. Anytime on this side, if we see a left subtree, we just take the value from the root. And then combine all these values and pick the largest one. And because we're visiting only log n number of nodes, we would know that we are only dealing with roughly log n number of values, and we can do this very efficiently. Because of the complexity of this, what I would suggest is for you to try and write down the code for this so that you see that you can actually do this fairly easily if you write it in a nice way. But it'll take you some time to kind of figure that out, and I do recommend trying to work it out for yourself. Okay. How am I doing with time? 42. Okay. So we should try and wrap up soon. Are there questions? You guys never asked me very many questions today. Was this a bit too much? What do you think? You think it was too much?
I think code complexity
Might be horrendous. Yeah.
The one thing to note is that for this problem,
Yeah.
they give you 1 second.
Yeah, so that you have to use a data structure similar to this. There is just no way you can do brute force searching and get the answers. There's just no way. That's the reason for making it 1 second.
It's just, and even n log n with a big constant factor might be too much.
Well, if you use a tree, then if you have an n log n algorithm, most likely it'll work. That would be my guess, because there's not that much you can make the constant large in the n log n algorithm.
I think this will be fine, but like I tried to implement it with segment tree.
And it didn't, and it blew.
pass.
Oh, okay.
Because what I didn't do all of this.
Yeah.
I handled by finding like the intervals are completely covered.
Okay. Yeah.
With like a
Yeah. So there, what happens is that the n becomes very large because you're taking each of the repeats as an extra item. If you compress it, then suddenly the array becomes very small and becomes manageable.
No, I did compress it. It's like first I did compression, but then like for the query, I think 4 to 9.
Yeah.
I converted it to 7, 7. And then
Okay.
what I did is to calculate the value of 3. I know it's 7 minus 4.
Yeah.
Is 3.
Yeah.
And then the right end will be 9 minus 7.
Right. Understood. Yeah.
And just segment tree on that.
Yeah. 4 becomes 7. 9 becomes. 9 becomes. Yeah.
And that just gave me too much of a constant.
Yeah.
That thing I was using too many insets. Like 2 or 3.
There may be something else with the segment tree that may be a problem. I don't know. That's the only thing I can think of. You had a
Sure.
question? Give me just a second.
So, are we required to use a tree? one of the homework assignments, you had a similar problem, which was like, time was like n plus n, and it was just using two arrays. So one of the arrays.
Yeah, you can't work this out with arrays. It's not possible. There's no way you can do a log n with just arrays. It's not simply.
No, I said n plus n.
Yeah, and anything with n is not going to work out. At least here, the constraints are such that n is very large and log n is manageable.
In that one exercise, it's a little different because it's a non-directed graph. So you go from 1 to 2, you also go from 2 to 1.
It was not a directed graph. It was like homework tree.
Yeah.
Where it was like given an array of numbers, count the frequencies, so then we had another array that would keep frequencies, so it would be like you just put in it.
Yeah. Here, the processing the array is not the problem. Processing the queries is the problem, and the number of queries is so large that it'll choke you if for every query you do order n processing, and they will at least for this particular problem, the way things are going to be set up is that they're going to check whether you're doing sort of brute force searching, and that's going to mess you up. So without a tree, you're dead in the water. Yeah.
Trying to do something like counting
That's what he was asking about. Is it? That's what you're saying? Sorry?
Yeah, I mean, he was telling like given an array and array of
Yeah.
elements and
So
then-
counting sort is what we would do in order to even set this up. All that is fine. That's not where the difficulty is. The challenge is in answering the queries. I did counting sort in order to go from here to here. Okay, and then from here you build the tree structure. Without the tree structure, you cannot answer queries fast. That's the challenge. That's where the difficulty is. Because otherwise, again, you have to imagine that this array is also fairly large. For every query, if I go through this entire array in order to figure this out, then it's not going to fly. That's where you need that tree. And the tree makes it roughly log n for every query, order log n for every query. And what Ricky was saying was that even log n, you have to be a little more careful. And that's possible. So were you ultimately able to fix the problem, or
No, I just went with another solution.
sorry?
I just went with another solution.
Oh, you went with that. Okay. Okay. Yeah. Maybe what we can do is maybe I could try and spell out some pseudocode so that things could be done. Because we were a little. I was explaining everything conceptually, and sometimes that's not enough to write the code. Okay, let me see if I can do that next week. But next week is after Thanksgiving. Let me see if I can write that up and send you something by email. Okay. Shall we stop here? Thank you, guys.